Hello, my name is Kenneth Thompson, and today I'm presenting my idea for the Siemens Clean Energy Competition. My concept was to design a wind alternative to solar for a residential setting. Wind traditionally is very hard to use in a residential setting because of the turbulence and lack of laminar flow in an urban setting. To avoid these constraints, along with size, I decided to use the vibrations caused by wind to generate electricity instead of a traditional rotary electromagnetic design. To the right here, you'll see my proposed design made in AutoCAD. It consists of a two-beam cantilever with a body mass head and a piezoelectric biomorph at the base. These harvesters will then be applied into a modular array of 4x3. These work much like a solar cell. A solar cell on its own does not produce a lot of electricity. However, when combined into an array, can produce significant amount of power. This works in a much similar fashion. The single harvester cannot produce a lot of electricity. However, when strung together, can produce a decent amount of electricity. These panels can then be used on a roof as needed. Whatever is the size of your roof, you can put as many panels as you need and generate the electricity. A brief rundown of how this works is wind is blown on the body mass. The body mass is then excited and will move rapidly up and down, causing the auxiliary beam right here to bend rapidly. This will then induce stress upon the main beam. The mechanical stress on the main beam is applied then to the piezoelectric. The piezoelectric, through its crystalline effect, will generate AC electrical energy. This AC can then be distributed directly to the grid or used directly by home appliances such as your refrigerator and stove. The AC can also be converted into DC using some sort of inverter to be used for home DC storage. Here is a simulation done in SolidWorks, a flow trajectory map. It is used to give similar results to a wind tunnel. I used a single harvester to see the effects of wind on the harvester. Here you'll see 4 different categories of results. One is wind pressure on the object, another wind and gravity stress, strain, and displacement. Something to look out for the most is the stress constant, which is a quite significant number. Another thing you'll notice is that the stress is evenly distributed amongst the main beam. This will cause a higher efficiency in the piezoelectric sheet. A brief rundown on materials. Acrylic was chosen for the body mass. This is because this is made from very thin stainless steel, and if you were to make this too heavy, it would gradually bend the cantilever out of shape, reducing efficiency of the design over time. Again, as I said before, it's a stainless steel cantilever. The reason behind choosing stainless steel is due to Hooke's law, which shows the strain to stress ratio is the highest in steel, which is great for our application. A piezoelectric sheet is used, PNPT to be specific. This is currently the highest efficiency single crystal piezoelectric available on the market and happens to work very well when applied with stress values. This will conclude my brief overview. I hope you enjoyed it. Take care.